Millions of people log into consumer AI platforms every day, type a question into a clean, simple chat box, and get an answer. It feels effortless. But underneath that interface is a massive engine routing raw data through complex, highly constrained operational nodes. Interacting with AI via casual, unstructured sentences is no longer a viable competitive strategy. To deploy AI successfully at scale, organizations have to stop operating as passive consumers. They must become active builders who master the actual execution layers of the technology. How well an AI performs, and exactly how much it costs your company, is dictated by three invisible mechanics: token economies, prompt architecture, and task routing. We are going to build an enterprise system from the ground up, starting with the atomic unit of AI data and culminating in a deployment strategy that drops operational overhead by 80%. Failing to master these underlying data mechanics removes the control necessary to prevent hallucinations, secure compliance, and stop the bleed of financial resources at scale. It is natural to assume that a machine reads human text the way we do, processing it letter by letter or word by word. It does not. Large language models process language using distinct structural fragments. These fragments are known as tokens. As a rule of thumb, one token is roughly equivalent to 4 characters of English text, or 3/4 of a single word. To an AI, chinchilla is read as 3 distinct blocks: chin, chill, and law. Common phrases like the cat remain unbroken blocks, while corporate jargon is aggressively chopped into multiple fragments. These tokens are the literal currency of the AI landscape. Providers do not charge a flat monthly fee for enterprise usage. They charge a fraction of a cent per token processed, meaning tokens dictate your operational billing and your system latency. They also dictate system memory. Every AI model has a hard physical ceiling on its memory capability, known as the context window. The context window represents the absolute total number of tokens a model can read and write at one single time. Because that capacity is finite, as new data pours in, the earliest data gets pushed out. If an executive attempts to upload a 2 million token corporate database into a model that only has a 1 million token limit, the system suffers amnesia, deleting the earliest data to make room. If operational leaders fail to measure their workflows in tokens, they surrender control over both their budget and the memory integrity of their system. Knowing how a single token works is the first step. The next step is organizing massive blocks of tokens to build a reliable corporate workflow. This requires treating text instructions with the precision and rigid structure that developers use to write software code. The discipline is known as context engineering. You cannot rely on a single flowing paragraph. A reliable enterprise prompt must be broken into 3 distinct operational zones: the system prompt for rules, the data layer for context, and the user query for the specific task. The system prompt sits at the top, locked down to establish the immutable rules, persona, and security guardrails of the AI system. Regular end users cannot easily change the system prompt. By locking this zone down, the organization ensures the AI remains safe and on-brand, regardless of the daily tasks requested in the user zone. When designing those rules, engineers must avoid the pink elephant problem. Giving an AI negative constraints, telling it what not to do, frequently fails. If you explicitly forbid a concept, like do not include competitor pricing, you force the neural network to mathematically process the concept first. This increases the likelihood it gets included in the final output anyway. The strict operational fix is positive framing. Instead of stating what the AI shouldn't do, you explicitly detail the exact documents or actions it must utilize, like exclusively utilize our internal pricing tables listed under Section 4. For complex tasks, the highest return tactic for stabilizing outputs is few-shot prompting. This involves inserting perfect examples of ideal inputs and outputs directly into the prompt text before asking the AI to perform a task. There is a nuance to keep in mind regarding modern reasoning models. These models possess built-in, native processing loops. They think automatically before rendering text. Instructing these modern models to think step by step is redundant. Relying on unstructured prompts creates unpredictable corporate liability. To connect these engineered contexts to an actual AI engine, companies use an API, or application programming interface. An API functions like a standard wall outlet. It allows internal corporate software to tap into multi-billion-dollar compute power without forcing the company to buy physical servers. Using that wall outlet introduces the first critical financial dynamic of API billing, the disparity between input costs and output costs. Processing text sent to the machine requires significantly less computational power than generating brand new text word by word. Because of this, output tokens are billed at a rate 2 to 5 times higher than input tokens. The immediate business strategy here is simple. Force AI outputs to be highly constrained and structured. Bullet points are literally cheaper than winding paragraphs. The second major financial mechanic solves the problem of repetitively querying massive, static corporate documents, like a 300-page employee handbook. This is called prompt caching. When the API detects that the first 5,000 tokens of your prompt are identical to a previous query, it bypasses full processing. It is read directly from local memory, applying up to a 90% discount. Understanding this input-output cost disparity and leveraging caching mechanics alters the basic profitability math of scaling AI across a massive employee base. Even with optimized prompts, there is an operational flaw in how many organizations route their tasks. They treat all corporate tasks as equal in complexity and send every single one to an expensive, flagship AI model. To prevent this overspending, organizations use model cascading. This strategy categorizes AI into 3 distinct operational tiers: premium reasoning models, moderate workhorse models, and fractional cent flash models. Model cascading deploys the cheapest, fastest model as a triage manager. Simple queries are resolved instantly at the flash tier for pennies. Only a small trickle of complex data drops to the bottom layer. The escalation trigger is strictly mathematical. Premium reasoning models are only invoked when a query is flagged as highly complex. This tiered approach guarantees that premium compute power is never wasted on menial categorization tasks. Failing to cascade models is the equivalent of using a nuclear reactor to power a single desk lamp. It guarantees massive, unnecessary financial inefficiency. We see the compound effect of these architectural strategies by applying them to a practical scenario. Consider an operations director tasked with automating 10,000 incoming customer support tickets every day. The unoptimized approach routes all 10,000 tickets directly to a flagship model, running a massive, unstructured raw text prompt every single time. This brute force method causes daily API bills to skyrocket into the thousands of dollars, while producing highly unpredictable output quality. Now, we deploy the same scenario, utilizing strict context engineering and API cost management mechanics. Through model cascading, the flash tier instantly resolves 8,000 basic tickets. Remaining complex tickets route to the workhorse tier. There, a structured prompt architecture triggers the prompt cache at a 90% discount, achieving identical quality with an 80% reduction in overhead. AI mastery is found in engineering rigid data flows, leveraging token economies, and designing structural business leverage from the ground up.